Today we will discuss applications of the various rules of probability that we derived. For example, addition rule, multiplication rule, the conditional probability, Bayes theorem, the concept of independence of events, etc. So, let me start with the one application of the general addition rule. Let us consider the problem. So, 6 cards are drawn with replacement from an ordinary deck. What is the probability that each of the 4 suits will be represented at least once among the 6 cards? So, here we are assuming that the deck of cards is well shuffled. There are 52 cards and 4 suits represent spade, heart, diamond and club. So, if we are drawing, so we draw a card and we put it back. So, after noting down the color of the suit of the card, we put it back in the deck and again we draw. So, this way it is called sampling with replacement. So, the event that we are interested is that out of 6 cards, the 4 suits are represented at least once. Now, if we try to find out the probability in the straightforward fashion, the possibilities are too many. For example, there could be 4 spades and there could be 1 card of each, and then the remaining 2 cards could be of any combination. They could be spade, heart, both could be spade, one could be spade, one could be diamond and so on. So, the number of possibilities is too many. Here we will show that if we make use of the idea of complementation as well as the union of the events, then the problem is somewhat simpler. So, let us consider the event A as that all the suits appear at least once. Then A complement denotes the event that at least one suit does not appear. Now, once again if we try to decompose it directly by saying that exactly one suit does not appear, exactly 2 suits do not appear, exactly 3 suits do not appear, then once again it is going to be a complicated event. So, we represent this as a different union of B I is equal to 1 to 4, where B 1 denotes the event that spades do not appear, B 2 denotes the event that hearts do not appear, B 3 denotes the event that diamonds do not appear, and B 4 denotes the event that the clubs do not appear. So, now by the addition rule, probability of A complement is equal to sigma probability of B I minus sigma double summation probability of B I intersection B j, where I is less than j and the summation is going up to 4. And plus triple summation probability of B I intersection B j intersection B k, where I is less than j less than k and the sums are going up to 4, minus probability of intersection B I is equal to 1 to 4. So, we need to evaluate the probabilities of all the terms appearing in this expansion of probability of A complement. Let us consider say probability of B I. So, here I will need to consider probability of B 1, probability of B 2, probability of B 3 and probability of B 4. Let us consider probability of B 1. Now, B 1 is the event then the none of the 6 cards is a spade. Now, if none of the cards is a spade, that means in one draw of a card there are 13 spades. So, if it is not a spade, then the probability of that is 39 by 52, that is 3 by 4. Since the drawing of the cards are independent and identical, because it is with replacement. So, every time there are 52 cards. So, the probabilities will be simply multiplied. It will be 3 by 4 into 3 by 4 6 times, that means, it is becoming 3 by 4 to the power 6. Now, if you notice here that if we replace this word spade by say club or by heart or by diamond, then the argument remains the same. Therefore, probability of B I for I is equal to 1, 2, 3, 4 is 3 by 4 to the power 6. Now, in a similar way, if we consider the event say probability of B 1 intersection B 2. Now, B 1 means that the spade do not appear, B 2 denotes the event that hearts do not appear. So, B 1 intersection B 2 means that in drawing of the card, spade and heart do not appear. Now, in a deck of 52 cards, 26 cards are for spades and hearts. So, in a single draw, if it is not a spade or a heart, the probability is half. Therefore, in 6 independent draws with identical setup, the probability becomes half to the power 6. Now, this probability remains the same if we replace say spade by hearts, the diamonds by clubs, etc. So, for all the combinations of spade heart, spade club, spade diamond, heart club and diamond heart, this probability of B I intersection B j is half to the power 6. Now, in a similar way, if we consider 3 of the suits do not appear, then the probability will be simply 1 by 4 in a single draw, and it will become 1 by 4 to the power 6 in 6 draws. Therefore, for all the combinations of I, j, k, for I less than j less than k lying between 1 and 4, probability of B I intersection B j intersection B k will be 1 by 4 to the power 6. The last term here is probability of intersection B I. However, what is the probability of intersection B I? Intersection B I denotes the event that none of the suits appear. However, if you draw a card, it has to be one of the suits. Therefore, the probability of intersection B I must be 0. Now, we substitute these probabilities in the general addition rule. So, there are 4 terms of probability of B I. Each of them is equal to 3 by 4 to the power 6. Then, if we look at the second term, which is having the probability of intersection of 2 events, then out of 4 there are 2 selections here, where I is less than j. So, it is 4 C 2 combinations. So, there are 6 such cases which have probability half to the power 6. If we look at intersection of events 3 taken at a time, then out of 4 we can choose them in 4 C 3, that is 4 possible ways, and the probabilities of these are 1 by 4 to the power 6. The last term is 0. Therefore, the probability of A complement, that is equal to this expression, which after simplification turns out to be 317 divided by 512, and approximately it is 0.62, and therefore, probability of A becomes 1 minus this, that is equal to 195 by 512 or approximately 0.38. So, the answer to the question that each of the 4 suits will be represented at least once is 0.38, which is less than 40% basically. Let us look at one more application of this general addition rule. If 4 married couples are arranged to be seated in a row, suppose there is a long table where these people 8 persons who are actually basically 4 married couples are to be seated, what is the probability that no husband is seated next to his wife? So, if we analyze this event directly, let us call the pairs 1, 2, 3 and 4, then the possibility that no husband is seated next to his wife will lead to various combinations. For example, husband 1 seated next to wife 2, husband 1 seated next to wife 3, husband 3 seated next to wife 4, and so on. The total number of possibilities is too many, and it will be a enumeration problem. However, we can simplify this by considering complementary event and then making use of the unions of events. So, let us define the event E to be that no married couple is together. then E complement denotes the event that at least one married couple is together. Therefore, E complement can be written as union of I is equal to 1 to 4, where AI denotes the event that ith couple sits together for I is equal to 1, 2, 3, 4. Notice here that this is a clever way of representing the union, because the other way of representing the union could have been union of B I is equal to 1 to 4, where B 1 event would have meant that one married couple sits together, B 2 would have meant that two married couples sit together, etc. However, evaluation of the probabilities of those events would be equally complicated, whereas here you will see that this representation leads to an easy calculation of the probabilities involved. Let us consider, say, the general addition rule. So, like in the previous problem, probability of E complement becomes sum of the probabilities of individual events minus double summation probability of intersection of two events taken at a time plus triple summation probability of three events taken at a time minus probability of intersection of all of them taken together. Now, the next step is to evaluate probabilities of individual terms here. So, if we look at probability of AI, then AI denotes that the ith couple sits together. Now, in order to evaluate this, we can make use of the classical definition of the probability, where we look at the favorable number of cases and the total number of cases. So, since there are 8 persons to be seated in a row, the total number of permutations in which they can sit is 8 factorial. Now, if I treat ith couple as one entity, because if I am saying that they sit together, then it can be on the left or the right. Therefore, the total number of arrangements that we have to consider is for only 7 people, because 6 persons and then 7th and 8th, that is the ith couple, it is considered as one individual, and we have to put that together somewhere along with those 6 people. So, the total number of arrangements can be 7 factorial. Now, here the place of husband and wife itself can be interchanged, that is in two possible ways. So, the total number of possibilities become 2 into 7 factorial, which is favoring to the event that the ith couple sits together, and therefore, the probability of AI is simply 2 into 7 factorial divided by 8 factorial. And of course, this argument is valid for any of the ith couple, that means for I is equal to 1 to 4. Now, if we extend this argument and consider the event AI intersection AJ, that means I am saying ith couple and the jth couple sit together, and we are not concerned about the other couple. So, there are 4 persons left plus 2 couple, which will be treated as 2 entities. So, there will be 6 persons, and these 6 persons can be arranged in 6 factorial possible ways. Since in this arrangement 2 of the persons are basically couple, and therefore, each of them can interchange their places, which can be done in 2 square ways, because in one of the ith pair the husband wife can interchange their places in 2 ways, and the jth pair the husband wife can interchange their places in 2 ways. So, 2 square. So, the favorable number of cases becomes 2 square into 6 factorial divided by 8 factorial. So, and this will be true for all pairs of I and j. In a similar way, if we consider ith, jth and kth pairs of couple sit together, then the total number of arrangements could be only 5 factorial into 2 cube. Let us look at this. If we have fixed the 3 couples, then one extra couple is left, whom we are treating as separate. So, there that is 2 persons, and these 3 couple will be considered as 3 persons. So, the total number of persons will be 5. Therefore, these people can be arranged in 5 factorial ways. Now, in each pair the husband wife can interchange their places, and therefore, each of them will have 2 extra arrangements. So, 2 into 2 into 2 3 times. So, the total number of cases of that ith, jth and kth couple sit together is 2 to the power 3 divided by into 5 factorial divided by 8 factorial. Finally, if I say that all the 4 couples sit together, then basically it will be arrangements of only 4 persons, 4 factorial plus all the husband wife pairs can interchange their places among themselves. So, that is 2 to the power 4 divided by 8 factorial. Now, if I look at here, probability of A I is this term and this is appearing 4 times. Probability of A I intersection A j is this term and this is appearing 4 C 2 times. Probability of A I intersection A j intersection A k is this term and this is appearing 4 C 3 times and this term is single term. So, if we substitute all these values, probability of E complement after some simplification turns out to be 23 by 35 or probability of E turns out to be 12 by 35, that is approximately 0.34. So, if we look at our original problem, what is the probability that no husband is seated next to his wife is 0.34, which is quite high. That means, in a random arrangement of 4 couples which are to be seated on a row on a long table, then the probability that none of the pairs are together is approximately 0.34, which is more than 1/3. So, which is substantially high. Let us look at one more problem where we consider the splitting of the event into various possibilities and then using the concept of independence, etc. So, consider rolling of a die. So, 3 players A, B and C, they take turns in throwing a die in order A, B, C, A, B, C and so on. That means, firstly the player A throws the die, then player B throws the die, then player C throws the die, then player A throws the die, then player B throws the die and so on. In this particular random experiment, we are interested to find out the probability that A is the second player to get a 6 for the first time or A is the last player to get a 6 for the first time. What is the interpretation of the first event? A is the second player to get a 6 for the first time. That means, either of B or C get a 6 before A in this sequence of trials. So, we analyze this event. Consider A to the throws of A. Now, A gets a chance the first trial, the fourth trial, the seventh trial and so on. That means, he gets to throw the die on 3 r plus 1th trial for r is equal to 0, 1, 2 etcetera. However, on the first trial itself he should not throw a 6, because he will not be then in second pair, then he will become a first player. So, r is equal to 0 is ruled out for him to get a 6. So, in order that he is second to throw a 6, it can be on any of the 3 r plus 1th trial for r is equal to 1, 2 and so on, not on r is equal to 0. Now, for r for the player A, he is getting r plus 1 trials, because in 3 r plus 1th trial he is getting a 6. That means, before that he is able to get r trials, each of A, B and C they get r trials. So, the player A, he should not get 6 on first of the r trials. Now, in a single trial, if we are assuming the die to be fair, A will not be able to throw a 6 with probability 5 by 6. So, in the first r trials, he is not able to get a 6. So, the probability that he will not get a 6 is 5 by 6 to the power r, and in the r plus 1th trial he gets a 6. So, the probability of that is 1 by 6. Now, out of this total 3 r plus 1 trials, player B and player C also get r trials to throw. out of this either of B or C must get a 6, then only A will be a second player to throw a 6 for the first time. Let us consider the case that B gets a 6. So, if we consider the probability that B does not get a 6, it will be 5 by 6 to the power r, because in each trial he will not be able to get a 6 with probability 5 by 6 to the power 5 by 6. So, the total probability that in r trials he does not get any 6 is 5 by 6 to the power r. So, if we consider 1 minus 5 by 6 to the power r, this is denoting the probability that he gets at least 1 6. So, now if we consider B is getting at least 1 6, then C must not get a 6. So, on each of his r trials, C will not get a 6 with probability 5 by 6 to the power r. Now, the entire event can be split, that you have A, B, C, etcetera, and this is the r 3 r plus 1th trial. So, here A gets a 6, and before that there are r trials for A, r trials for B, and r trials for C. In the r trials for A, there is no 6, therefore, the probability of that is 5 by 6 to the power r. For C, there is no 6, therefore, the probability for that is also 5 by 6 to the power r. So, the probability becomes 5 by 6 to the power 2 r. For B, he gets at least 1 6, therefore, the probability is 1 minus 5 by 6 to the power r. On the last trial 3 r plus 1th trial, A gets a 6 and the probability for that is 1 by 6. Now, here if we look at this probability, this is the probability that on one particular 3 r plus 1th trial, A gets a 6, before that B has got at least 1 6 and C has not got a 6, and A also does not get a 6 before that. This is denoting the total probability for this event. Now, here you can notice here that we have made use of the concept of independence of the trials, because all the probabilities have been multiplied. This is total probability for the 3 r plus 1th trial in this particular fashion, that no 6s for A and no 6s for C and at least 1 6 for B, and the last trial 3 r plus 1th trial is a 6 for A. Now, here r can take any values from 1 to and so on. Therefore, the probability that A is the second to throw a 6 after B, but before C. Now, we can interchange the role of B and C here and we will get the same expression. Therefore, the actual probability that A is the second player to throw a 6 will be 2 times this, because it incorporates the possibility that C is first, A is second and B is third, etcetera also. Now, we can simplify this expression. This is 1 by 3 into sum of one geometric series minus sum of another geometric series, infinite geometric series with the common ratio either 5 by 6 square or 5 by 6 cube. So, we can evaluate this, and after simplification it turns out to be 300 by 1001, which is nearly 0.3. That means, in this particular sequence A will be the second player to throw a 6 for the first time is nearly 0.3. See, here we can also look at the event that A is the first player to throw a 6, then A must be able to throw it on the first trial, on the fourth trial, etcetera. If he throws on the first, definitely it is 1 by 6. If he is throwing on say fourth trial, then before that none of the other players must be able to throw a 6. That means, A himself is not able to throw, B is not able to throw, C is not able to throw. So, this probability is simply a infinite geometric series that is equal to 1 by 6, 1 by 1 minus 125 by 216, that is equal to 1 by 6, and 216 minus this is 91, that is equal to 36 by 91. That is probability that A is the first to throw a 6. If we try to compare it with this one, then it is 11, 11, 99, 99 plus 100. That is 396 by 1001. So, you can see that the probability got reduced. Since A is the first player to get a chance for throwing, the probability that he will be the first to get a 6 is much higher, that is 396 by 1001, corresponding to as A is the second, that is it is 300 by 1001. The probability is reduced. Let us also see A is the last to throw a 6. If he is last to throw a 6, then once again he will be able to throw a 6 on 3 r plus 1th trial for r is equal to 1, 2 and so on. On r is equal to 0, he must not throw a 6. So, once again no 6 on r throws, that will be 5 by 6 to the power r, and r plus first throw is a 6 with probability 1 by 6. And if he is last to throw a 6, that means both B and C must be able to get at least 1 6 in their r trials, which are held before the 3 r plus 1th trial. So, using the argument which we gave in the first part of this problem, probability that B throws at least 1 6 in r trials, that will be 1 minus 5 by 6 to the power r. And in a similar way, probability that C throws at least 1 6 in r trials, that will be with probability 1 minus 5 by 6 to the power r. Thank you.